So let's start today's video, which will be the detailed calculation method for the short circuit calculation, balanced three-phase short circuit calculation, single line to ground fault short circuit calculation using the manual method, and I will validate using this ETAP software. And this is the model. If we consider this source grid, next one is this two winding transformer. If these two items are connected, then what will be the fault level at 11 kV bus? If there is a short circuit, voltage short circuit fault at this 11 kV bus, what will be the fault current contribution from the source grid through this two winding transformer in this 11 kV bus? It's a very simple network, and we will be using this Excel file. So let's check this grid. This is source grid, and the base MVA, as you can see, this is 100 MVA. So we will mention the base MVA as 100 MVA. So this will be the unit. And base kV, what will be the base kV? This is 110 kV, 110 kV system. Grid size is 110 kV. So we will take the base kV as 110 kV as well. Okay. So now we will calculate, we will try to find out the grid parameters. So grid parameters. What is the grid voltage? Grid voltage 110 kV. Grid short circuit current. This is considered as 40 kiloamps. So this is 40 kA. Next, the grid X by R ratio. What is X by R ratio? That is 14. 14, and unit is unitless. There is no unit for this X by R. And for our calculation, we will use not only X by R, we will use R by X ratio also. So what is R by X? That is equals to 1 divided by X by R. Okay. Now, first of all, so these are the inputs. These are the inputs for the grid, right? These are the inputs. Now we need to find out what is the short circuit MVA. MVA SC. If we know this voltage and short circuit current, we can find out the grid short circuit MVA, which is √3 kV into √3 into kV into short circuit current. That means equals to square root 3 multiplied by voltage multiplied by the short circuit current So this one MVA. So this is short circuit MVA. Now what is the percentage Z? Now the percentage Z value of source means grid side, that is equals to base MVA by short circuit MVA into 100%. So base MVA, that is equals to base MVA, which is nothing but 100 MVA, base MVA by short circuit MVA into 100% into 100. So this is 1.312%. This is in percentage. So this is percentage Z. Now how to calculate the percentage R value and percentage X value? If we have percentage Z, we can find out firstly Z is PU, means per unit value, per unit impedance, that is equals to this divided by 100. So 0.01312 unit is per unit PU. Now we have the source impedance per unit value. Now we need to calculate R is PU. R is PU. So to calculate this resistance value, source resistance value in per unit, that is equals to Z per unit into MVA new by MVA old. Sorry, I made a mistake. We need to we have Z is per unit value. Now if we want to calculate the RS per unit, that means we need to use the formula considering this Z value. So this will be Z per unit equals to this Z per unit divided by, within bracket, 1 plus divided by 1 plus x by r square, right? X by r whole square. One by, sorry, square root of this. This is also in per unit. What I have done, we have the impedance Z value in per unit. We need to calculate R value in per unit. We have X by R ratio as 14. So resistance value in per unit equals to this impedance, means Z per unit divided by square root of 1 plus X by R whole square. Similarly, X per unit equals to Z per unit divided by square root of 1 plus R by X square whole square, 1 plus R by X whole square. This is also in per unit. So we have got these two figures. Let's highlight it because this is required for the to find out the positive and negative sequence values. This is R value, this is X value of the grid in per unit. So we have done this, and let's check with the ETAP software what is this. So R value per unit is 0.309348. Here R value 0.09349, but it is in percentage. It is in percentage. Percentage R. If we convert it in per unit, that means this divided by 100, so it will come 0.309349. Here it is 0.30934875, so rounding of 0.309349, and percent, and this per unit value of reactance X 0.013, it is in percentage, so if we divide by 100, it is coming 0.0130883, 0.013088251, rounding of 883. So it is matching with this ETAP input. So we have done for this grid. We have done this part for this grid. Fine. Next, we need to analyze the parameters for this transformer. So let's go for this transformer part. Transformer rating is 25 MVA, 110 kV per 11 kV system. So we will do now. Transformer rating 25 MVA. Okay. kV primary 110 kV. kV secondary, this is 11 kV. Okay, and what is the percentage impedance and X by R ratio? We will check. Here percentage impedance is Z is 10% and X by R ratio is 20. These are the inputs. So if we write percentage Z, that is 10%. Next, X by R is 20. There is no unitless. So what is R by X? What is R by X? Equals to 1 divided by X by R, which is 0.05. Right. Now we need to calculate the resistance values because impedance value is provided. Let's insert another row. So what will be the ZT PU per unit impedance equals to percentage divided by 100. So this is in PU. So we have transformer impedance Z value is 0.1 PU. We need to calculate RTPU and XTPU, transformer resistance per unit value, transformer reactance per unit value. So how to calculate? Using the same formula, we can calculate resistance value equals to impedance value in per unit divided by square root of 1 plus x by r to the power 2. So 0.00499, this one is per unit. And similarly, reactance value is equal to this ZTPU divided by square root 2 square root of 1 plus r by x whole square. This is in pu. So r value 0.00499 pu and x value 0.0998 pu in per unit. But we cannot use this resistance value or this reactance value along with these grid parameters. We cannot directly add this r value with this grid r value and x value of this transformer with the grid x value. Why? Because the MVA base MVA is different. For this grid, the base MVA is 100 MVA. For this transformer, the base MVA is 25 MVA. So we need to convert this transformer 25 MVA base into 100 MVA base, right? So now we need to change change the base, change in base for transformer. So how to change this base? So now this RTPU transformer per unit, this new value, that will be the old equals to the old value, old resistance value multiplied by, can you recall the formula what you have gone through in your college days, that the change in base, impedance, new impedance equals to the old impedance into base kV, kV old by kV new whole square into MVA new by MVA old, right? So we don't need to consider the kV old or kV new value because this is same only, this is 11 kV only, but we need to consider the new MVA which is 100 MVA, and the old MVA as 25 MVA, right? So the new value of RT, transformer resistance, will be the old value of R multiplied by new MVA divided by old MVA which is 25. So this is coming 0.0199. This is in per unit value. This is in per unit. And similarly, what is the value of transformer reactance at the PU new value? That is equals to the old value. This is the old value multiplied by base MVA new base MVA new, that is 100, divided by base MVA old, that is 25. So it's coming 0.3995. 0.3995, this is also in PU. So we have got, based on the 100 MVA base, this is the transformer resistance value in PU. This is the transformer reactance value in PU per unit. Now we need to consider another thing, which is transformer impedance correction factor. Which is transformer impedance correction factor. What is that? Impedance correction factor, which is K suffix T. Impedance correction factor. What's the formula of impedance correction factor? Impedance correction factor is KT equals to 0.95. Let me write the formula here. KT equals to 0.95 multiplied by C max divided by 1 plus 0.6 into X trafo. 1 plus 0.6 into X trafo, XT, right? So this is the formula to find out the value of KT, right? Let me write here. Sorry, this is the KT value. So equals to KT equals to 0.95 multiplied by C max. C max value is 1.1 as per IEC. This is as per IEC formula, C max. So 0.95 into C max divided by 1 plus 0.6, 0.6 into XT. XT means before the change in base. Before changing the transform base, that means we need to consider this XT value, not the corrected one, not the changed one. We need to consider this old value based on this transformer. So we should be careful about that. People make mistake about this. Okay, so this is coming 0.9859. This is coming 0.9859, right? This is the value of KT. So now we'll find the corrected values of R and X, right? So RT PU corrected, RT PU corrected equals to this multiplied by this correction factor, temperature correction factor. This is in PU obviously, and this is the value of X. This is equals to this old value multiplied by this impedance correction factor. This is also in PU. So the corrected values of R is 0.019, right? And this is the X value. So let's highlight this value also, because the transformer and this grid, these are in series. As seen from this 11 kV faulted bus, the source grid and this transformer, these two are in series. So we need to add these impedances, means this R value, grid R value with this transformer R value, this grid X value with this transformer X value. So because these are considered now in common base of 100 MVA base. So this part is also completed. This transformer part is also completed now, right? So now what we'll do, we will find out the value of the three-phase short circuit current. To find out the three-phase short circuit current, we need to find out the value of Z. So what will be the value of Z? Means Z1, positive sequence impedance, value of Z1. So to find out the Z1, we need to the value of R1, which is the summation of this source R add this transformer R, that is in pu per unit value, and this x1 equals to source x plus transformer x, this is also in pu per unit value. So what is the value of z1? Z1 equals to, so we know that R1 value and we know this x1 value also. So this is equals to square root of this square plus x square, right? Yeah, so this is in pu, this is in pu. So we have got z1, value of z1, and what is value of z2? z2 z2 is equals to z1 only, z2 equals to z1 only here in this case, because if you see in ETAP also, this z value, this positive sequence resistance and reactance values are same, equals to negative sequence resistance and reactance. Also for this transformer, if you check this impedance part, this positive sequence resistance and reactance values are mentioned. There is no negative sequence because this is static device, so they have not considered the negative sequence as well, and zero sequence impedance is considered here. And z1 and z2 we have found out. Now what is the value of z0, z0? So z0 equals to, so to find out the z0 value, we need to check what's the connection, transformer winding connection here. This is DYN, delta star transformer. This is delta star solidly grounded transformer. If you see grounding part, this is delta star, and so this is delta star solidly grounded system. So for this, if there is any ground fault, if there is any ground fault at this 11 kV bus, the zero sequence path is not continued, that is discontinued here, because the transformer primary side is delta connected. That means there will be no zero sequence path, and we should not consider this source grid impedance for this to find out this z0 value, right? So what I am trying to say, this z0 equals to, what will be the value of z0? We should consider the value of square root of this transformer only, not the source. That means this square root square plus this impedance is square, right? So Z0 is, this is in PU obviously, so 0.3943 and this Z1 equals to Z2, Z1 equals to Z2. We need to highlight this because we need this in this data for the calculation of three-phase fault and single line to ground fault as well. So we have find out the Z1 value of Z1, value of Z2 and value of Z0, right? Now we will find out the three-phase fault current, three-phase fault current. So to find out the three-phase fault current, we need to find out the current in PU, means per unit current value, per unit fault current. So IFPU equals to V by Z1. V by Z1. Z1 is also per unit and V also 1 per unit. So we are considering, we are using the per unit system here. So V is 1 per unit and Z1 is this one per unit. So 1 equals to 1 divided by Z1. So this is 2.45. Again this is in PU. So this is the fault current in PU. What is the, now we need to find out the base current. What is the base current? The formula of base current is nothing but the base MVA by root 3 into base kV. Once again, the base current equals to base MVA. What is that? Base MVA equals to 100. Base MVA is 100 divided by square root 3 multiplied by voltage base kV. So this is 0.5248, but one thing we need to check here, this is in MVA, base MVA, and this is in kV. So unit we need to multiply it by 1000. So what is this? I base equals to base MVA divided by square root 3 into base kV. Sorry, this is not the kV. Actually we need to consider this base kV because we are considering at 11 kV system fault, 11 kV system. So it will not be this base kV. We are considering 11 kV side. So now the base kV should be 11, right? And this 1000 will not, this multiplied by 1000, that means this is ampere, and we need to mention in kiloampere. That means this 1000 will not be there. I will clarify this point. What is this? This base MVA, this is in kiloampere. What is this? Base MVA, that is 100 MVA divided by root 3 into base kV, means 11 kV system. Now our base kV is 11 kV because we are checking the fault current at 11 kV side. If it was in 110 kV side, then the base kV will be 110. Now we are working in this 11 kV side. That means base kV is 11 kV. So MVA by kV, so it is coming kiloampere. So 5.24 kiloampere, this is the base current. This is the base current. So what is I fault current actual? Sorry. IF actual fault current. Actual fault current equals to this per unit fault current multiplied by this base fault current, which is coming 12.88 kiloamps. This is in kiloamps, obviously. This is in 12.88 kiloamps. So let's check in ETAP how much it is coming. We have created a fault here. Let's check the fault current. What is coming here? 14.123, and here it is 12.88 kiloamps. So why this mismatch is coming? Because of the C factor. Because of the C factor, here they have considered 1.1 as per IEC standard, so it is 1.1. So with C factor, it will be multiplied by 1.1. So 1.1 multiplied by this actual fault current, so this is coming 14.168 in kiloamps, right? So this is the final result for three-phase short circuit current, 14.168. Here it's coming 14.123. So 14.123, 14.168. So this much of difference is coming only, but it is almost matching with this manual calculation. Now we will calculate the single line to ground fault also similarly for this SLG fault. For SLG, single line to ground fault. To find out the single line to ground fault, what to do? To find out the single line to ground fault, we need all these three values, Z1, Z2 and Z0, and we need to find out the IF PU, this per unit fault current. This equals to, for three-phase fault current it was V by Z, right? It was V by Z. I equals to V by Z. But for single line to ground fault, this I will be, this equals to 3V. If you can recall the formula for this ground fault current, I0, I know 3V divided by Z1 plus Z2 plus Z0, right? This is the formula. So I0 equals to 3V by Z1 plus Z2 plus Z0, right? So 3V means 3 into 1 per unit. This is equals to 3 into 1 per unit means 3 divided by Z1 plus Z2 plus Z0. So it is coming 2.48 obviously in per unit. Now the base current will be same. So base current equals to base MVA divided by square root 3 into base kV means 11 kV side, this much of kiloampere. This is kiloampere. So what will be I actual fault current? I actual will be, this equals to this per unit value multiplied by this base value, that is 13.02 KA, 13.02 KA, and obviously we need to consider C factor, and we will validate in ETAP also, equals to 1.1 multiplied by this actual fault current. It is coming 14.322 kiloamps, 14.322 kiloamps. Let's check in ETAP how much it is coming. This is 14.123. This is three-phase fault current. And what is the single line to ground fault current? Let's check. This is 14.291. 14.291. It's coming 14.322. There is a slight difference, but it is almost matching with this manual calculation. So in this video, you have learned how to calculate this, how to find out the grid parameter, how to find out these transform parameters, and changing the base, and to consider how to consider this impedance correction factor, find out the Z1 value, Z2 value, and Z0 value, and finally finding out the three-phase fault current considering this Z1 V by Z1, basically positive sequence, only positive sequence impedance, what is the three-phase fault current, and what is the single line to ground fault current considering this Z1 plus Z2 plus Z0 values for this star delta connected, for this delta star connected solidly grounded system. If it is star star grounded or star delta connected, then the value of Z0 will change, and accordingly there will be no change in three-phase short circuit current, but there will be change in single line to ground fault current. Why? Because the value of Z0 will get changed. That is the thing. But there will be no change in Z1, value of Z1 and Z2. So that's why there will not be any change in three-phase fault current if the winding connection is different. But this will be changed. Single line to ground fault will be changed. So in this video up to this is the basic thing we should know, otherwise we will be called as the tool operator if we use only this ETAP software or any other similar type of software. If we just put the parameters and we are getting the results, we will not be able to analyze properly, so that we will be called as the tool operator. So we should not be a tool operator. As a power system engineer, we should know how the software is operating and how it is calculating the values, and whether the values whatever they are giving, whether these are correct or not. So that analysis part we need to understand. So this was the very basic thing to find out, to perform the short circuit analysis, and I have validated using the ETAP software. So in this video up to this, in the next video I will show by connecting one motor of 5 megawatt motor by cable connection. Okay, so that will be covered in next video, and accordingly what will be the total short circuit current contribution at this 11 kV bus. And subsequently there will be another video where I will discuss if we connect this 10 MVA lump load, so what will be the total short circuit current contribution. So in this video up to this.